Welcome to the Strategy Room. If you're here, you already know that Cambridge physics can sometimes feel like the boogeyman of grades. It pushes you out of your comfort zone. And today, we're going to teach you exactly how to push back with perfect examiner-approved answers. We are going to systematically decode the invisible rules governing everything from a balanced ruler to a deep-sea diver. Think of two types of students facing these exact physics concepts in the exam hall. First, there's Alex. Alex overloads their answers with raw physics facts, dumping every formula they know onto the page, but provides absolutely zero analysis of the actual scenario. Then there's Sam. Sam rushes the questions, panics at the sight of a complex diagram, and completely misses the specific command word requirements the examiner is looking for. Both approaches lead to a sea of red ink. Today, we are going to fix that. We're building a clear, structured understanding of forces, density, and pressure, and we're going to look at exactly how to structure your answers to secure every single mark. Let's dive in.
Here is our strategic roadmap for the fundamental A-level physics concepts we are going to break down today. We'll be moving smoothly from the mechanics of rigid solids all the way to the behavior of fluids. First, we'll tackle turning effects and moments. Second, achieving physical equilibrium. Third, defining density and pressure. And finally, we will wrap up with liquid pressure and upthrust.
Let's jump right into Section 1, Turning Effects and Moments. We are going to start by looking at the invisible forces that cause rigid objects to rotate, and exactly where students lose easy marks on this topic.
A crucial term you absolutely must define accurately in your exam is the moment. Now pay close attention here, because this is where Sam always loses a mark. What is really interesting and absolutely critical is the necessity of using the perpendicular distance in your calculations. If the examiner asks you to define a moment and you just write force times distance or the torque around a pivot, you get zero, nothing. Precision is your ultimate weapon here. The official, mark scheme-approved definition of the moment of a force about a point is the magnitude of the force multiplied by the perpendicular distance of the line of action of the force from that specific point. You literally cannot skip the word perpendicular. Let's look at exactly how this traps students when real numbers are involved.
This image brilliantly illustrates that exact definition in practice, and it's a classic setup for a Cambridge exam question. Look at the spanner on your screen. The force applied by the hand is 30 newtons, and the total length along the spanner itself is 0.25 meters. Now, if Alex was answering this, they would instantly rush in, multiply 30 by 0.25, write down 7.5 and move on, and they would be completely wrong. Why? Because the 30-newton force is applied at a 20-degree angle to the perpendicular. It is not a straight push. To get the correct answer, we must find the actual perpendicular distance from the pivot, which is the center of the nut, to the line of action of that force. If you look at the geometry and draw a triangle, the perpendicular distance is that dashed line labeled x. Using basic trigonometry, x equals the hypotenuse of 0.25 multiplied by the cosine of 20 degrees. When you crunch that, it gives us an effective distance of 0.235 meters. Now, and only now, we apply our strict definition. The moment equals 30 newtons multiplied by 0.235 meters, which gives us a final moment of roughly 7.05 newton meters. And a pro tip, never ever forget to write your SI units.
Now, what if the examiner decides to level up the complexity? A massive conceptual trap that catches out thousands of students every year is confusing a single turning force with a couple. If you compare a single force to a couple, like when you turn a steering wheel with two hands or turn a tap with two fingers, you will see that a couple is highly unique. A couple strictly produces rotation without any linear acceleration whatsoever. Think about it. A single force acting off-center on a free-floating football might cause the ball to spin clockwise, but it will absolutely also accelerate the ball linearly across the pitch. A couple, however, consists of two perfectly parallel forces of equal magnitude acting in opposite directions with lines of action that do not coincide. It only spins, it doesn't travel. Before we continue, subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGSC to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now.
All right, let's move into Section 2, Achieving Physical Equilibrium. Transitioning smoothly from simple rotation, let's explore exactly what it takes for an object of finite size to achieve a state of perfect, unmoving stillness.
If a question asks you to state the conditions for equilibrium for a rigid body, you need a perfect two-part answer. Simply stating that the forces balance out is far too vague and will cost you points. The crucial concept for true physical equilibrium is that these two distinct conditions must both be met simultaneously. First point, the resultant force on the object must be exactly zero. This guarantees it is not accelerating linearly in any direction. Second point,
The resultant torque or resultant moment on the object must also be exactly 0. This guarantees it is not accelerating rotationally. Resultant force is 0 and resultant torque is 0. One without the other is not equilibrium. You must state both to secure top marks.
Let's see this in action with a classic paper 4-style scenario. By applying the principle of moments to this uniform meter rule, we can visually see how equating the clockwise and anti-clockwise moments allows us to mathematically deduce the exact pivot position for perfect balance. Let's act like examiners and solve this together. The ruler itself has a weight of 1.20 newtons. The absolute key word here is uniform. Because it's a uniform object, you immediately know its center of gravity acts exactly through its midpoint, the 50 centimeter mark. Now, a weight of 1.50 newtons is hung at the 10 centimeter mark. We need to find the specific pivot position labeled x to achieve equilibrium. We set up our equation. The sum of clockwise moments must perfectly equal the sum of anticlockwise moments. The clockwise moment is generated by the ruler's own weight pulling down on the right side of the pivot. The distance from the pivot is 50 minus x centimeters, so the moment is 50 minus x multiplied by 1.20 newtons. The anticlockwise moment is from the hanging weight on the left. Its distance from the pivot is x minus 10 centimeters, so that moment is x minus 10 multiplied by 1.50 newtons. Equating those two sides and carefully doing the algebra reveals that x must be exactly 27.8 centimeters. This is how you secure maximum marks. Methodical, step-by-step logic.
But what happens when forces aren't just acting up and down on a flat 2D ruler? What if you're dealing with a complex system of forces acting at strange angles? This is where vector triangles come in. When dealing with multiple coplanar forces, you can visually prove equilibrium by following these exact steps to draw a closed vector triangle. The golden rule here is that all the arrows must flow sequentially in the exact same continuous direction. Listen closely, because this is where Sam completely falls apart. The instinct when drawing vectors is to draw a resultant vector from start to finish. But remember our rule for equilibrium? The resultant force must be 0. Therefore, there is no resultant line. The arrows must chase each other in a continuous loop, bringing you right back to your exact starting point. That perfectly closed geometrical loop is your visual and mathematical proof that the net force is 0.
Let's apply this to a high-level data scan challenge. This geometric framework turns a complex real-world scenario, like a tethered helium balloon straining against a 10 kilonewton braking force, into a simple, solvable closed triangle. Look closely at the diagram. We have an upthrust of 8 kilonewtons pushing vertically upwards. We have a mysterious horizontal wind force pushing to the right. And we have the tension of the tether pulling down at an angle, with a maximum braking limit of 10 kilonewtons. To find the maximum wind force it can withstand, we draw our closed triangle. You draw the 8 kilonewton upthrust pointing straight up. From the tip of that arrow, you draw a horizontal construction line to represent the wind. Then, from the start of your very first arrow, you use a compass scaled to 10 kilonewtons to strike an arc on that horizontal wind line. Connect the dots, ensure the arrows chase each other in a loop, and you have your answer. By measuring that horizontal line, or using Pythagoras since it's a right angle, we find the maximum wind force is exactly 6.0 kilonewtons. Stop scrolling. Subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2-3 grade boundaries. Join them right now by subscribing to @theexams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions.
Let's transition into Section 3, defining density and pressure. We are shifting from the macroscopic mechanics of levers and balloons to the internal properties of materials and surfaces.
Here is a prime example of where you need to find the flaw in your own thinking before the examiner does. Imagine you write down that pressure is the force acting on an area pushing in a downward direction. Did you spot the error? It is incredibly easy to confuse pressure with force, but remember that pressure considers the area it acts upon, and fundamentally, it operates purely as a scalar quantity. Force is a vector. It has a magnitude and a specific direction. Pressure is a scalar. It has magnitude, but absolutely no specific direction. It acts normally, which means exactly at right angles to any surface it encounters. But the pressure itself doesn't have a built-in directional arrow. A pressure of 1 Pascal is simply defined as a force of 1 Newton acting normally on an area of 1 square meter. Lock that definition into your memory.
Let's test that with a speed writing challenge scenario.
This stamped coin example is a fantastic micro-narrative showing how an enormous pressure of 2.8 times 10 to the 5th pascals distributed over a tiny area translates directly into the 106 newtons of force required from the heavy machinery die. If you face this in the exam, your structure needs to be perfectly clean. First, calculate the area of the circular metal coin. Area equals pi times the radius squared. The problem gives a diameter of 2.2 centimeters, which means a radius of 1.1 centimeters. Now, here is the trap. You must convert that to meters immediately. Leaving it in centimeters will ruin your entire calculation. Converting it gives a radius of 0.011 meters. Squaring that and multiplying by pi gives an area of roughly 3.8 times 10 to the negative 4th square meters. Then, knowing our formula that pressure equals force over area, we simply rearrange it. Force equals pressure multiplied by area. So, 2.8 times 10 to the 5th pascals multiplied by our tiny area gives us exactly 106 newtons of force. Notice how methodically we stepped through that? That is the strategy for maximum marks.
Finally, let's plunge into Section 4, Liquid Pressure and Upthrust. We're going underwater to master the mechanics of fluid dynamics and buoyancy.
In A-level physics, you can't just memorize the final formula like Alex does. You are often required to derive it from scratch. By looking at the physical weight of this exact column of water, we can systematically derive the critical equation that pressure equals density times gravity times height. You start with the absolute basics. The weight of the water column is equal to its mass times gravitational field strength, or W equals mg. Next, you substitute mass with density times volume, because mass is just how dense something is multiplied by how much space it takes up. Then you break volume down further. The volume of a cylinder is its cross-sectional area multiplied by its height. So the total weight equals density times area times height times gravity. Finally, since pressure is defined as force, in this case weight, divided by area, you divide that whole massive expression by A. The areas on the top and bottom cancel out beautifully, leaving you with the elegant final formula. Pressure equals density times height times gravity. P equals rho GH.
Now, I need your absolute focus here because this specific detail is one of the most common places to lose marks on a 9702 paper. A massive study tip to remember is that a diver descending into the ocean doesn't just feel the weight of the seawater above them, they also have the entire weight of the Earth's atmosphere pressing down on the surface of that ocean. If an exam question asks you to calculate the total pressure on a diver at a depth of, say, 24 meters, you first calculate the liquid pressure using our newly derived rho GH equation. For dense seawater, that might come out to around 2.4 times 10 to the 5 pascals. But if you stop there, you fail the question. You absolutely must add the atmospheric pressure, which is usually given as around 1.01 times 10 to the 5 pascals, to get the true total pressure acting on the diver. Do not forget the sky above the sea.
Let's look at how to perfectly structure a written explanation for upthrust. If the command word is explain, you need a logical step-by-step breakdown. This logical flow on screen perfectly explains the invisible mechanism of upthrust. Point 1. Establish the rule. Hydrostatic pressure naturally increases with depth. Point 2. Apply it to the object. Because of this, the bottom surface of any submerged object is always at a slightly greater depth than its top surface. Point 3. Connect to force. Since pressure equals force over area, the upward force acting on the deeper bottom surface is inherently greater than the downward force acting on the shallower top surface. Point 4. The link. This fundamental difference in opposing forces creates a net upward resultant force, which we officially define as upthrust. It's simply the natural, unavoidable result of pressure increasing with depth, effectively pushing the object upwards from below. That is how you structure a top-tier paragraph.
To bring this entire system together, here is your high-yield cheat sheet summary table of the absolute must-learn equations from this unit. You need to commit these to memory. We have our standard foundational equations for density and pressure, positioned right alongside our derived fluid pressure equation, and the resulting upthrust equation. Ensure you know not just the letters, but exactly when and how to apply each one of these effectively depending on the scenario. Students who implement these physics strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to @acetheexams_IGCSE and click that bell. Don't let another exam pass you by.
I am going to leave you with this final, explosive thought on Archimedes' principle to help you visualize just how incredibly powerful displaced fluid can be. If you push a large beach ball underwater, it shoots back up. Why? Think about the massive volume of heavy water that is being displaced by the ball, compared to the tiny, almost negligible mass of the air actually inside the ball. The resulting upward upthrust force is absolutely massive, while the downward weight pulling it down is minimal. Drop a comment below with your target grade for physics and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the exams. Your Cambridge success starts here.